Hey, do opposites really attract? Join me for Networking 101 and find out. You know, we're going to get about as 101 as you can get when it comes to electronics, because what is it that flows through this thing, right? What is it that goes through this cord or through the copper wires of this thing? What is it? It's that electricity, right? It's that kind of magical element that we seem to kind of overlook when we're doing network design, right? I mean, as engineers out there, we're looking at the most basic level, we're looking at ones and zeros, right? That's what our networks look like. That's what they displace. But the reality of it is, what is a one? What is a zero? What is it that make that up? That's the electronics, right? That's the beauty of all this that makes everything out here happen, right? It's almost, describing electronics is almost like describing the force, right? It's that energy that goes through us and it binds us to the universe, right? And that's what really, I absolutely love about this job is all the electronics. So let's kind of go back. Let's take a step and find out how this stuff works. Well, when you look at it, and look, please, don't think that this is way too complicated and that you can't learn stuff, because everybody can learn the fundamentals of electricity and really get a lot out of all the gear and everything that you're using here just by understanding some real basic concepts. Electronics is kind of cool, because what happens is that as we're sending electricity across the wire, our first piece is actually this wire. And what is it that conducts, or what makes one piece of wire work when other ones don't, right? Typically, when we look at wire like the cable I threw down, we'll call it copper, right? Copper wire is a very good conductor. As a matter of fact, it's probably the second best conductor we have out there. There's really four main conductors when we're looking at electronics. It's silver, copper, gold, and aluminum. And they pretty much conduct in that order, if you will, as far as how they work. Now, I know you've probably heard some people say that gold is better, and I'm telling you that engineers to engineers are going to argue which one is better, gold or silver and that kind of stuff. To me, I look at the resistance and the resistivity of it, and silver is by far the best. It's also the most corrosive. I mean, it tends to oxidize and lose its resistance pretty quick, but we're getting kind of way off in the weeds here. So let's just say that this is how it is, and then once you start digging into it, you can kind of find out which one you like the best. But what is it? Why are those better? Well, electronics is so cool because it has elements of all kinds of disciplines of science, chemistry, physics, everything else. And so these four, and there's a bunch more than that too as well, these four are picked because when you look at what they're made of, actually from an atomic level, you know, and you're looking at them, it's this outer ring, what we're calling an outer valence. This outer valence is considered unstable. It has one or two electrons in it. And these atoms, they want to stabilize themselves out. So they're willing to give this electron up. And they are so willing to do it that when you hit them with just a little bit of electricity, they will flow these electrons like crazy. So much so we call that an electron sea. And that electron sea is, as we hit this with a little bit of electricity, that current will flow like crazy, right? Of course, I got my current wrong. I'm doing it the Benjamin Franklin way. It flows from negative to positive. But what you're looking at is our conductors, the easier they can give up these electrons is how much quickly we can flow this current through, how effective it is, how little resistance we're actually going to use. And that's how we deliver that information to our target. The next piece of this puzzle is that now that I can get this flowing, what are some of my principal elements? And there's a whole bunch of them, right? But really the big ones that you kind of need to know is a simple equation that we call Ohm's law. Ohm's law was actually invented by a dude named Dr. Ohm. And what it really amounts to is that you have voltage, or we symbolize that with an E, over resistance by current. R is actually our resistance side, and our current is what we represent with I. Now, probably there's two good ways to look at this in an analogy. The way I like to explain electronics or electricity when you're looking at it is something a little more tangible, is that it's water flowing through a pipe. Now, I know a lot of double E's out there will probably cringe when they hear it because a lot of people hate that analogy, but I kind of like it to explain how wires and the outer jacket, the insulator works, is that I have to have a place to go. I have to have some space for that water to actually flow. And that space in here, in this example, is where we want this current to move through. As this current is moving, we're actually going to call, as that electricity travels, we call that current. As we restrict this, and make this just a little bit thinner so we can kind of put like a little chicane in here, if you will, and we can tie that up. As we're making this pipe a little bit smaller, then that smaller piece in here is actually what we're calling resistance. And that resistance piece in there is its ability to kind of hold back that current or that voltage a little bit, right? So that's what we're looking at holding back in here. And then the voltage itself is what is actually, the amount that's getting through, right? So that's our voltage piece that's happening. When we're looking at these ones and zeros in our network, this is called logic. This logic is actually represented by how much voltage that we're getting through. Now, this logic can be what we call negative logic or positive logic. And that really, from a networking design perspective, it doesn't matter too much, but what you need to look at here is you're dealing with some very, very small voltages. Sometimes they're low as 0.7. Sometimes the highest I've seen on some of the older ones is 3.3 volts. And considering that we take, 120 or 220 inside of our equipment, that's a lot of voltage to drop off here, right? So that's the basis of how you're toggling this information back and forth, is you're basically removing a ground or adding a ground to this, so that you're having, if it's got volts going through it, then it's a 1. If it doesn't, then it's a 0. It's turning it on and off, right? That's basic electricity, is really what we're looking at here. Now, in this water pipe analogy, if you look at that, as we're getting this to flow through, this is a really pretty important piece to understanding what our electronics is like. But a lot of people will look at this and are like, yeah, but I don't necessarily see the correlation. Well, because our water is flowing through here, we're actually going to call this our conductor. It's moving right through. The outer jacket on here, if you're actually looking at this, if we're going off and we're saying that this is no longer X-rayed and you're looking at the outside of it, the ability for the water to stay inside of here or not go on the outside, to kind of stay in one place, is actually what we're calling the insulator, right? That jacket, that piece right here, red on this piece here, is keeping that voltage from not traveling through here. This will not conduct as well because it actually does have a lot more atoms, a lot more electrons in its outer valence. So it's a very stable type of atom. So it's not going to want to give these up unless you put a whole bunch of energy into it to start kicking these out. But for the most part, very poor conductors, great insulators. It means I can grab this with my hands and I'm not going to get shocked or anything like that. So that's what makes a good insulator to make that work. To see electricity in motion, I think one of my favorite analogies, again, we talked about the water piece, but to actually see everything work and how this works in distance and how we get that instantaneous response is, let's say you got a couple gears here. So I got gear 1 and gear 2. And if I run a belt, let me change my colors here. If I run a belt across these gears, and then I put a handle on this, and I start turning this. As you can see, as I'm starting to turn this handle, and let's say that at this end I've got a weight attached to it. The second I start moving this out, just even the tiniest bit, I'm going to see this weight move. It'll move up or down depending upon how I'm actually, adjusting or messing with that crank. And that's how electronics works, right? This is basically, as I'm turning this, as I'm actually increasing that load, this piece here is my current. It will respond instantaneously to anything I put to it. So you're looking at something that the second you put the voltage to it, boom, it's to actually start working right now because it's all attached, it's all system. And that's what really Ohm's law is telling you, is that this is really one big beautiful system that makes, all these binary bits flow and make everything happen. I'll tell you what, there is probably not too many things I enjoy more than electrical engineering. I absolutely fantastically love it. And I think that probably in my library, I've got maybe 5 books that I consider ready references that sit on my desk, and I actually use them consistently, and I can walk by and pick them up like a comic and sit there and read them just to kind of grab some information. And one of those books is one of my favorites. It's actually called Electrical Engineering 101, and the subtitle is that everything you should have learned in school, but you probably didn't. And it's by a guy, Darren Ashby, that's a good guy. He's got his email address in here, and he'll respond to emails if you email him and stuff. If you're starting in electrical engineering, if you're interested in it, if you just want to know a little bit more about how those ones become ones and how zeros become zeros, pick this book up. You can get it on your e-reader, anything else. I absolutely love it, man. For engineers out there just kind of learning it, you just can't get better than this.